Section 7.3 Trigonometric Substitution. In this section, we're going to talk about the integrals that requires a substitution of a trigonometric functions, which is summarized in the table of the lower part of page 478 of our textbook. In this table, the expression square root of a squared minus x squared, square root of a squared plus x squared, and finally square root of x squared minus a squared are given. And for those substitutions, x equal to a sine of theta, x equal to a tangent of theta, x equal to a secant of theta are given respectively. And finally, the identities associated with those are given. And let's talk about how to utilize this table in actual situation. And let's do that through the notebook. Here we go. Trigonometric substitution. And here is the table reproduced right over here. Square root of a squared minus x squared, the most important case. Then what we do, we take x equal to a sine of theta. Consequently, taking the derivative, we're going to get dx equal to a cosine of theta d theta. Now, how does that help? If I plug in x equal to a sine of theta into this expression, this simplification is what you're going to end up with. A squared minus a squared sine squared of theta. And after factorization, we get 1 minus sine squared. What is 1 minus sine squared? That's cosine squared. Consequently, a squared and cosine squared can come outside the square root, and this is what you get, a cosine of theta, but inside, this square root has to be greater than or equal to 0, so we have this absolute value sign. Most of the time, this absolute value sign will not cause too much trouble because we are going to deal with definite integrals, and the interval of the definite integral will take care of the sign. Most of the time, in particular interval, the cosine will turn out to be positive, so you don't really have to worry about the absolute value sign. Very rarely we can think about some situations where we have entirely negative. I haven't written any kind of example like that in my career. That dates back to 1994. So you probably won't have to worry about those kind of things. And the kind of examples where pluses and minuses are intertwining, well, I have never seen anywhere at all, so please don't worry too much about it. In short, if you miss this absolute value sign, you're not going to miss anything. If you do the same thing to the second expression with substitution, x equal to a tangent of theta, we're going to get something like this. X is going to be replaced by a tangent of theta, so squaring and factoring, what do you get? We have 1 plus tangent squared. That's the same as secant squared. Consequently, a squared, secant squared can come outside the square root, and we end up with this secant function. Again, most of the time, this absolute value sign won't cause too much trouble. Finally, if you have x squared minus a squared inside the square root, we take x equal to a secant of theta, and dx equals to a secant of theta tangent of theta d theta, and then the inside of the square root can be simplified kind of like this by the Pythagorean identity. Secant squared minus 1 is tangent squared, so we end up with this a tangent of theta again. So what do we have in the end? The square root expression will be gone, and we are going to get simpler integral. Let's move on to an example problem, and let's move directly to 3.2, the most important example, or maybe I can say the only important example to tell the truth. Okay, x squared over a squared plus y squared over b squared equals to 1. This expression defines an ellipse. Ellipse kind of given like this, kind of elongated circle where the right hand side is a comma 0, the left hand side is negative a comma 0, the top is 0 comma b, and the bottom is 0 comma negative b. In this particular example, I took a equal to 3 and b equals to 2, but if I select different numbers, like kind of like that, then we're gonna get different ellipse like this. I just changed b equals to 5, so the stretching is even further in vertical direction, and it's a little bit too big, so let's change it back to that. Oh, by the way, if I take same values for a and b, then I'm gonna get a circle. Okay, let's go back to where it was. Okay, how do I find out the ellipse? Excuse me, how do I find out the area of the region enclosed by the ellipse? Here's a nice strategy. Because of the symmetry, take this yellow part in the first quadrant and then simply multiply by 4. And that's gonna make this integral problem much simpler in a couple of important reasons. One is, well, okay, we are talking about smaller regions, so it's good, it's better, but much bigger reason is the top, the blue part and red part are actually different functions. And this expression over here is implicit equation, and in order to do some computation, you'll have to solve for y and get an explicit expression, excuse me, y equals to some function of x, kind of like that. And this is y squared we are talking about, so if you take square root somewhere, you're going to get plus and minus square root. Consequently, we have top function blue and bottom function red. And this yellow picture, this picture over here with this yellow region suggests that we don't have to deal with both of them. We only have to look at one of them, the blue one, the positive. Indeed, here's the computation. We begin with this implicit expression, flip this x squared over a squared to the other side, generating this, and then flip this b squared in denominator, generating that expression, and then finally take the square root. So b squared over a squared becomes just b over a, and this inside of the parenthesis becomes square root of a squared minus x squared, and we have plus or minus, but that's okay. Plus will give me blue function, minus will give me red function, and we're going to concentrate upon this yellow region over here. So we'll just look at blue function. Consequently, we can just ignore this negative sign and work out only positive. In short, we have this kind of integral and the integrand. Please note that integrand has just positive, no negative there. Okay, simply multiplying by 4 of that to this integral, we're going to get the area. And how do we calculate this integral? Well, trig substitution will be helpful because we have square root of a squared minus x squared. Take x equal to a sine of theta and then plug it in, and this is the computation we have. A squared minus x squared equals to square root of a squared minus a squared times sine squared. So following the same computation as before, we're going to get a squared times cosine squared inside square root. So after taking it out, we have a cosine of t and absolute value. Now, how did I lose this absolute value in the end? Let's answer that question here. That's because cosine function is always greater than or equal to 0 in this particular region. And that's coming from this observation. Integral is running from x equal to 0 to x equal to a, isn't it? When x equal to 0, a sine of t is 0, so we take t equal to 0. And that's when we're going to get x equal to 0. As a matter of fact, the direction of these arrows are backward, I have to say. In order to get x equals to a, we start from t equals to pi over 2. In that case, sine of pi over 2 is 1, so a sine of t is a. Consequently, we have x equals to a. So the integral, x is running from 0 to a, is now transformed into the integral where t is moving from 0 to pi over 2. And here they are. The first integral is the original integral. X is running from 0 to x equals a. And I just took b over a outside, and the square root is there. The blue square root is the same as a cosine of t, as we did before. And we don't have to deal with absolute value sign, because in this particular interval, theta is between 0 and pi over 2. Cosine function is positive. And dx is a cosine of t dt by derivative computation, yes. And what we have just in t integral, which can be simplified like this. A squared is multiplied into this b over a, so we have a times b, and cosine squared. Now, integral of cosine squared, we have done this before many times, actually back from calculus 1. How do we handle this? We use the power reduction formula, 1 plus cosine of 2t over 2, and apply the antiderivative formulae, and we have, well, this expression, t plus 1/2 sine of 2t. I'm missing something. This should be 4. Excuse me, that should be 1/2, but extra 2 is coming out because of the chain rule. Well, it didn't make any difference here, luckily, because whether I plug in t equals pi over 2 or t equals to 0, the sine part will become 0 anyway. So only this one will make any difference. So in the end, what do we have? We have pi ab. That actually fits our common sense very, very well, because if you go back to that original picture here, the area of a circle, area of the region inside of a circle is pi r squared. Kind of like this, pi r squared. And then, better start from 1, pi r squared. And then if I stretch this circle of radius 1 horizontally by 3, then I'm gonna have to multiply 3 to this area, because everything is stretched horizontally. So in general, if I multiply by a, then I'll have to multiply by a to pi 1 squared. Now, if I multiply 2 vertically to stretch this a little bit flatter ellipse vertically to create a final ellipse, then I'll have to multiply 2 to the area as well. In general, I'm multiplying with b. So we started from pi r squared, pi 1 squared, so it's from pi, multiply by a and multiply by b. Consequently, we get pi ab. And that was geometrical explanation, kind of transformation type of explanation for area formula for an ellipse. Horizontal stretching and then vertical stretching. In terms of calculus, we can find out the area kind of like this using the trigonometric substitution. Well, here goes the only important example. And the other examples are, what can I say, left to the student. You can open up some of those problems and then go through with those problems. Here I have x squared minus 1, so it's going to be secant. Here it's going to be a little bit more complicated, t squared minus 6t plus 13 in square root. So if you use complete square formula to change that into this form, t minus 3 total quantity squared plus 2 squared, then you can see how to do with this kind of things. T will be t minus 3 will be 2 tangent of theta or something like that, and the rest is left to the students.